Hello, everyone. My name is Zeyu. I'm currently a PhD student at Yale University, advised by Professor Ben Fish. And my research is in general cryptography, with a focus on lattice-based cryptography, especially FHE and its applications. So the talk of today will be relaxed functional bootstrapping, a new perspective on BGV and BFV bootstrapping. It's a joint work with my colleague Yun Hao. Okay, so let's get started. Of course, I believe all of you attending this FHE meetup should be familiar with what FHE is and what bootstrapping is. But for the sake of the completeness, I'm still gonna give some background on FHE and bootstrapping. So suppose you have some data X, and you encrypt it under your secret key, and you get a ciphertext encryption of X. And what the FHE allows is that it allows you to evaluate some function f over this encrypted data X, and you will obtain encryption of f of X. However, there's a special property for all the existing FHE schemes is that the input ciphertext usually comes always comes with some noise. And after you evaluate some function f, the noise will accumulate. And after it gets to some threshold, I would call it like the noise budget is used up. In this case, you will not be able to further evaluate some function f of say f of prime. If you do this, instead of getting what you want, you will get some encryption of noise or like just random values. This is, of course, not what you really want. So there's a procedure called bootstrapping. And this bootstrapping procedure, essentially, what this does is that it brings down the noise by some amount. So it frees up some noise budget. And then, but without changing the content encrypted under the ciphertext. With this, you will be able to further evaluate the function f of prime, and then you will be able to obtain encryption of f prime of f of x, as you would expect. This all sounds perfect. And also, I would like to quickly mention that I forgot this x can be, say, a bunch of data. So it can be a vector of data, and this f can be a multivariate function. So does this f prime. Okay, this all sounds great. What's the problem? So the problem is that it's very inefficient, the bootstrapping procedure. So it's inefficient from two aspects. The first is that the bootstrapping circuit by itself is very complicated. It can be even more complicated than this function f or f prime. So basically, the time you are waiting for this bootstrapping is even longer than the time you are doing the work you want to do. Right. So. And another aspect of bootstrapping that's in the inefficiency of bootstrapping is that bootstrapping does not do anything else. Right? So when I say does nothing else, I mean like it only brings down the noise. It only gives you more noise budget, but it doesn't change the content. So you're just waiting for the bootstrapping without doing any other work. Like it's a sort of wasting time. So in our work, we introduce we define and build what we call the relaxed function of bootstrapping, and it improves from two aspects. The first is that it allows a more efficient bootstrapping circuit, so the time for bootstrapping itself is lower. And the second is that it allows a free function evaluation during bootstrapping. So at least during bootstrapping, you can get some work done. So with this in mind, before we dive into what we do, we'll first briefly recap the BGV and BFV FHE scheme. They are both ring LW based. They work over this ring, Zx over Phi of x, and this Phi is the n cyclotomic polynomial. And the ciphertext has this following form, AB, which are just two ring Q elements, this ring mod some large value Q. And then this B satisfies AS, where AS is the secret, plus E is some small error, and plus some encoding of the message you want to encode. This PR will be clear in a second. The PR is the plaintext, denotes the plaintext modulus. So we have the plaintext space being ring mod P to the R for some value P to the R. And this message is within this ring P to the R. So this is the encoding for BFV, and BGV is slightly different. But for the sake of this talk, we'll just use the BFV one. They are proven to be equivalent, so it does not matter that much. Okay? And then if we have n being a power of 2, and if it satisfies that p mod 2n equals to 1, then the plaintext space, instead of being a ring element, we can just encode it to, we can just make it being a vector of zp elements for some prime p. So it's a vector of m values. So what we do is we will encode this m vector into some ring elements and then do the encryption. So this is very helpful, I think, in a lot of applications, because in real world applications, people more work beyond, like, say, finite fields rather than some large like medium to small size finite fields instead of like a large rings. And the basic operations are addition and multiplications, and as mentioned, we'll just work on this vector. So all this are done element wisely over the vector. These are just two simple illustrations. If you add two vectors, they are done pairwisely, and so does the multiplication. Okay. So past works in BGV BFV have been following this pattern. I don't expect you to read or understand. I think the main takeaway is that what they do is they temporarily enlarge the plaintext space from p to the r to p to the e for some e greater than r. And this basically sort of restricts the parameter choice, and this is not the case for our construction. Okay. So with all this background, I think it's ready for us to take a look at our formal definition. Okay, so first at a high level, we work over this zp to the n, a vector of zp elements, and then why we call this relaxed is because we only guarantee correctness for some x, the valid input set x, that's basically a subset of zp instead of the entire zp. Okay, so it means that if m is within this valid input set x, the output is f of m for some predefined function f that's mapping from x to zp. What happens to like the input that's not in this valid input set, we will discuss that in a second. Okay. And another requirement we have is that we want the output noise budget to be greater than the input noise budget. Of course, if this function f is non-trivial, it can also be interesting if the noise budget does not increase, because like basically it says that you can evaluate this function f for free without increasing any noise. But for the sake of this talk, or like in general, this entire work is focusing on the notion that the output noise budget is greater than the input noise budget. Okay, and as one can see, that the regular bootstrapping is just a special case of our definition. It basically says that the x is equal to zp, and this function f is an identity function. Okay, so one may ask, like, why is this relaxation reasonable? We believe that for lots of applications, we know the input in advance. So it doesn't matter if we don't guarantee the input being incorrect for other points that are not in this like subspace. Example 1. So for example, after a comparison, you want to do a bootstrapping. Then what you basically know that the output is always either 0 or 1. Right, so you only need to guarantee the correctness for these 2 bits, but other than that, it doesn't really matter. Another example is that suppose you can encode the data into x instead of encoding it to zp in general, then you can make sure that throughout the entire computation, the input remains in x. Then the bootstrapping can just be used to guarantee like the correctness of this x. Right? This can be interesting for applications like PRR or PSI. At the approaching the end of the talk, I'm gonna talk about a detailed application that's on oblivious permutation, which is a building block used for a PRR, private information retrieval construction. Okay, so this is our formal definition. I don't expect you to read or understand. I just want to emphasize 2 points. The first is that if this m is in this valid input set, we will guarantee that the output is correct as expected, f of mi. And the second is that we want to guarantee that the output noise budget is greater than input noise budget. Okay, these are the two main points of this definition. And as promised, we'll talk about what if M is not in this valid input set. What do we do? Well, in general, I would say we don't care. And this is indeed the core source of our efficiency improvement. So because we can we can allow this kind of this incorrectness. That's why we can improve our efficiency. But for the completeness of the paper, we did define a property which we call L closeness. It means that if this M is not within this X, okay, then we will output f of M prime, where this M prime is some value that's inside this valid input set, that's being one of the L closest elements to M. So this can be first, for some of our constructions we will talk today, they can achieve it for free. Some do not achieve it, and some achieve it with some costs. This property we believe can be used for some applications like privacy preserving machine learning, because you can basically bound the error using this L closeness. But for some other applications, especially the ones that we're going to introduce at the end, it doesn't really matter that much. So the definition of L closeness formally is as follows. Again, I don't expect you to read. The only thing I want to emphasize is here we define what do we mean by the L closest elements to M. It basically means that if you take M points in this X and you compute M prime minus M, they are the distance are the L smallest values. Okay, cool. With this definition, we'll go through our construction. We'll start with a simple construction first. So we'll define this valid input set to be a very structured set that's basically 0, R, 2R, 3R, up to P minus 1 minus R. And this ZP again is the plain text space. And this R is some value that we will talk about later, just as assuming to be some constant for now. And we also assume this R divides P minus 1, but of course, if it doesn't, it doesn't matter. Otherwise, we can just choose some R that's like round R to the nearest value that divides P, for example, or we can just set X to be 0 minus P minus C with step size R for some integer C instead of just P minus 1. Okay. And for this setup, for this starting point, we will set this function f to be an identity function. So as you can see, this setup is a strictly weaker. This construction will be strictly weaker than standard bootstrapping, because this X is a smaller space, and this f is just an identity function. Okay. Identity function basically means if input is M, we output M. Okay. Okay, this animation is a bit weird, but so this valid input set X is basically, as you can see, this axis is the entire ZP. Sorry for the typo, ZP, and then we're just taking a few points from this entire axis. Okay, cool. So with this setup in mind, let's try to build a construction for our relaxed function of bootstrapping. Okay, so given a ciphertext AB in ring Q, 2 ring Q elements, there's a missing 2 here, sorry, encrypting some message M and ZP. It should be encrypting a vector, but as mentioned, everything we've done in this work are done element wisely. So we're just focusing on a single element in ZP, and it applies to the entire vector as well. So we'll first modular switch AB to ring P, as that's encrypting M. That's encrypting M and ZP. Okay. So after this modular switching, as you can see, the ciphertext modulus and the plaintext modulus overlap. So what it means, it means that if M is within this valid input set, then M prime, this should be encrypting M prime. So this M prime will be within the range instead of just a single point. So let's take a look at this illustration. Basically, we have this valid input set being all these points. After modular switching, it will be mapped to, say, any point within this large range, not just a single point. Okay. So after getting this new ciphertext, what we can do is that first we try to homomorphically decrypt this new ciphertext A prime B prime. We'll obtain this M. m prime. So what I mean by decrypt, I mean just compute as plus as plus b, which is just a linear operation. This can be done using a linear transformation, a homomorphic entity. It's been widely studied by many works, so we will not go into the details, but it's just easily doable. You can also we also call this like partial decryption in our work, because it doesn't deal with the error, it just computes the as plus b. And then the next step is that we'll compute a post-processing function, fpost, that will basically map the range back to the message m for all the input value set. So again, the illustration, as you can see, we are just mapping this fpost will map the entire range back to a single point. So you can the difference from the last illustration is that the arrows direction changes. So it's essentially the same thing. Okay. This fpost can be interpolated as a degree p-1 function. And the correctness is achieved in a very straightforward way, because like these two graphs are just the same thing, except for the arrow. So an additional thing is that this construction achieves two closeness for free, because if m is not within this x, for example, if m is at this point, after module switching, it will be mapped to like either this orange one or this light green one, so when mapped back, it will be either mapped back to R or to R, like this is M or M2 here. So it achieves two closeness for free. But the main point is that this construction is relatively simple, and the correctness is very straightforward. Cool. With this starting point, let's deal with a more complicated case. Suppose now we have a slightly less structured valid input set that doesn't start from 0. It starts from some value u and with some value v. And the step size instead of r, it can be some arbitrary r prime, like for example in this illustration. Sorry, this should be a subset. And then we have this u plus r prime, u plus 2r prime, etc. We have these points. We allow arbitrary r prime. The only requirement we do is that the size of this x2 is not larger than the size of the x1 that we just presented. Okay, that r was the modulus switching error. Just to recap. Now we allow this function f2 to be an arbitrary function that can map x2 to zp. It's no longer an identity function. Okay? So the output will be f2 of m if m is within this valid input set f2 x2. Okay, so what's the issue now? The issue now is that because r prime can be arbitrary, that means that r prime can be a lot smaller than r. Then it means that the modular switching, if we do a modular switching, it will cause some error. Because like for example, u and u plus r prime can be mapped to a single point. Now you don't know how to map them back. So what we do now is that first we homomorphically evaluate some pre-processing function f pre. This f pre for this construction will just be mapping x2 back to x1. Okay. How this is achieved? It's achieved by the single function. We first normalize it by just subtracting x by u to make the starting point back to 0, and then we enlarge it by computing some constant. Right. So this can be easily done. If we naively evaluate this, it will cost one level of multiplication. Of course, it's still very cheap, but it can also be merged with what a process called a slot to coef. So this process, this pre-processing, is essentially for free. So if for those who are not familiar with slot to coef, it doesn't really matter. It's just something we need to do before we do our modular switch. Then we perform a Then we perform module switching, and then homomorphic decryption as before. We will obtain some m prime. That's again within some range that we showed before. Lastly, we want to get what we need and we need the new post-processing function. We cannot just use the post-processing function for x1, because first we now have this f2 that's no longer an identity function, and second, we want to evaluate f2 over x2 instead of x1. Okay, so this f2 will be f post 2 will be as follows. It will be basically it will just be, this part is the same as the original f post, but now we take into account we want to revert the pre-processing function, and we also want to evaluate this f2. This looks a lot more complicated than the first construction, but it can still be interpolated as a degree p-1 function, so it doesn't introduce any extra work. So basically, this second construction, although it's more general and more complicated than the first construction, they basically share the exact same efficiency, which I will also show in the benchmark part. So with these two constructions in mind, we're ready to just summarize our general framework. After we get some ciphertext CT, we'll first evaluate some pre-processing function to obtain some new ciphertext. We'll evaluate the slot to coef, which is just some decoding. And then we will do a module switching. And then we will perform this homomorphic decryption, which is just a linear operation. And lastly, we do some post processing, evaluate some post processing function to get what we need. Okay, this is our general framework, and all of the following constructions that I'm going to talk about will follow this exact general framework that's abstracted out from the previous two constructions. Okay, so with this, I'm going to talk about a few more constructions that are more fine-grained, less structured, and more general. So now let's define some point function x. Some set x3. This x3 is just y1 through yz. Now it doesn't have any structure like before. It doesn't need to be like a uv r with step size r prime. Okay. No, the only requirement we have is that the size is again small, at least not larger than the size of x1. Again, we also allow this f3 to be an arbitrary function. It can map y to any of the point in ZP. So now let's talk about how to define this pre-processing function. Naturally, we can just define this f pre to be a map from x3 to x1. Of course, only the first z elements. However, there are more efficient ways to do it when z is much smaller than p-1 over r. So if this is the case, then we can compute this function f pre 3 prime. That's just some constant w times this x. This will map this x3 to some new set x3 prime. And for maybe at least one of this value in ZP star, we will be able to obtain some x3 prime that have every point inside x3 prime that pairwise are well separated. When I say well separated, I mean like the difference between any 2 points in x3 prime is separated by at least r. So it doesn't need to be just r; it can be greater than r. So it doesn't need to be like So it doesn't need to be the same structure as this x1. Of course, this is a relatively heuristic, but at least for z much smaller, this should be probable. And in practice, this is also the case, as we will later show in our benchmark section. Okay, then f post 3 will be very similar to f post 2, except that now we only need degree z times r. This r is module switching error again. Instead of p-1. So if this z is small, the cost of this post-processing function will also be much smaller. That's the point function. We also, in the paper, we also talk about range functions. What do I mean by range functions? I mean this x4. Now we define the input value set x4 to be a bunch of ranges instead of just a single point. Okay. So in the illustration, is basically just this dark gray areas, which are just k different ranges. These light gray areas I will discuss in a second. So additional requirement we need is that these ranges are well separated. Okay, so the ranges, like basically this V1 difference between this V1 and U2 needs to be at least R, and this like-array part basically means that this has size like R/2. This basically means you have two, like if the two like-array parts do not overlap, they are separated by at least R. Okay, formally this is the K-wall separated ranges is defined by this. Okay, so now we allow this f4 to be arbitrary function, except that it's now mapping a single range to a single point instead of single point to a single point. So for any x within a range, it's mapped to the same point yj. Okay. To construct, now we have this preprocessing function can simply be an identity function because we don't need to map anything because everything is already well separated. Fpost is similar to fpost 3, except now it maps the entire gray area to a single value yi instead of just the range that's around one single point, but it's the entire range that's around this smaller, darker gray range. So the degree now has the size of x4 plus k times r. This will be this makes it first this is no longer restricted by the size of x1. So this can be very close to the size of zt. So in some cases it will be more efficient. Okay. For this range function, we also have this kind of special cases. Suppose we have only two ranges, but it's very unbalanced. Of course, they have to be well separated. But when I say very unbalanced, I mean like the size of the second range V1, U2 V2 is a lot larger than the first range U1 V1. Okay, then again, this construction can be extended to k ranges, but preferably with just one range much larger than the other ones combined. For the sake of this talk, we'll just focus on the two range case. And now we can again allow this f5 to be arbitrary function that's mapping one range to a point. And again, this f prime will be just a simple identity function. But now this f post will be slightly different from the original range function f post. It will first check if this x is within this range. If so, it will map to y1. Otherwise, it will just map to y2. So more formally, it can be written as follows. I will not go through the details. The main takeaway is that this function can be evaluated with just the size of the first range plus log p plus r operations. So this is a lot more efficient. For example, if this range is like 2 and this range is 10,000. Right. Using the idea from the previous slide, we will take at least 10,000 operations. But using this this new idea, you can just it only takes you 2 plus log p operations to evaluate this unbalanced range. Okay. So these are pretty much all the constructions that we introduced in the paper. As mentioned, that this can be extended to k ranges, and for this construction, it doesn't achieve first is trivially achieves two closeness because there are only two separated ranges. But for k1s, it doesn't achieve L closeness easily. And for some of the constructions we introduced, we will achieve it with some cost. But we will not go through the details because it's not super important for us. So now let's take a look at the benchmarks. So as you can see, no matter how you look at the runtime, if you look at the per slot runtime or per bit runtime compared to prior works, where others are acting faster. And for some constructions, so for example, this are the point functions with only 8 points. The pre-processing is like basically taking it's just a computing. As mentioned, we just compute a small scalar multiplication, which is very fast. Okay. And for the range functions, it can be even faster. It's even less than 0.1 millisecond per bit bootstrapped. This is the breakdown of the runtime. As you can see, for some constructions, like the first two basic constructions we introduced, the lookup table evaluation. The lookup table is essentially the post. The post processing function is taking most of the time, but for some of the constructions, actually the post processing function is taking very little time. So there are a lot of extra room for improvement. Like for example, the linear operation or slot to coef, which we just did it in the simplest way. So there are still, I think, a lot of room for improvement. Okay. So as promised, I would like to talk about one application in detail. I think this application is very suitable and I also believe it's quite interesting. Okay. This application is Oblivious permutation. This is one work from last year, CCS. A proposed way to do a homomorphic permutation. Okay, so what do I mean by homomorphic permutation? I mean, given a database of m bits, the server will randomly permute it without knowing the exact permutation after like how the client wants it to permute. What the server does is the server will perform what they call Thorpe shuffle, using some random bits that are encrypted under FHE. So first assume that there are a bunch of random bits encrypted under FHE, and then the server will use this FHE use the FHE with this random bits to homomorphically perform this Thorpe shuffle. I'll first introduce what's a Thorpe shuffle. Suppose you have like 8 database elements. You will first separate them into half, and then you will use a random coin to decide whether you want to flip the 2 bits. For example, the first coin you don't flip, and the second coin you flip, and the third and the fourth coin. After this, you will like basically decide pairwise whether to flip them and get a new database of 8 elements. Of course, this gives a permutation, but not yet a random permutation. So what the Thorpe shuffle does is that it will repeat this process for k times. So you will separate this new database into half again, and then repeat this process. This then will give a random permutation except with 1 minus negligible probability. And concretely, you need to repeat this process for like 400 times, which means that it will take you like more than 400 levels of multiplications. This is when the bootstrapping comes in. We'll talk about that in a second. And so for simplicity, we will, as mentioned, we just assume we have a bunch of bits, and in the work, the bits are generated by using some FHE-friendly PRG, and this work achieves a FHE-friendly PRG based on learning with error that can sample every bit using just roughly 0.3 milliseconds. So it can be done relatively efficiently. So the bottleneck will indeed be the bootstrapping part. Okay, so this is very suitable for our relaxed functional bootstrapping because we can encode the database elements into X. The example we're giving, the database elements are bits, so we just need a 1-bit size X. But we can also enlarge to allow the database elements to be, say, 3 bits. Then this X will just be some set with 8 elements. Okay, the second part that makes it very suitable for our relaxed bootstrapping is that it only requires swapping. So the swapping only changes the order of the elements. It does not change the content of the elements. So the elements throughout the entire computation process will remain in this X. Okay, so using this, using our relaxed bootstrapping instead of regular bootstrapping, we achieve an orders of magnitude efficiency improvement for this oblivious permutation construction. Of course, there are other interesting applications we discussed in our paper, but not in detail as we did it for the oblivious permutation, which are PIR, private information retrieval, PSI, private set intersection, or fuzzy PSI with computation. Of course, there's always the secure machine learning. And in this case, as mentioned, the closeness may be preferred because we want to make sure that the error is sort of bounded. Also of independent interest, we show that our techniques can be used to improve a batch view KFHG bootstrapping over a year from over work from Asia 23. That can improve it by like roughly 3 to 6x. Of course, there are lots of open questions. For example, like, are there additional function families we can, are there additional like a valid input set we can perform? Are there more efficient constructions? And are there more applications that are suitable? But that's pretty much it for today's talk. And this is the link of our paper. Thank you all very much for listening. I think I can now take questions.